Swayam Prabha. Digital India. Educated India.
Welcome back, students. So yesterday we were discussing about the non-ideality in reactors, where we first discussed about non-ideal reactors. So the two major type of reactors which we generally come across while designing is the plug flow reactor or the mixed reactor. Where the plug flow reactor is similar to the batch kinetics, and mixed flow reactor, the example is the continuous stirred tank reactor. So then we saw how to characterize the non-ideality in the reactor systems. So we then spoke about residence time distribution, and then how to find the residence time distribution. We spoke about the tracer experiments where different kinds of inputs can be given, and at the exit the profile is noted how the tracer is coming out from the reactor with time. So we discussed especially the two types of inputs. One was the pulse input and the other was a step input. Then where we came across the F curve and how E curve is related to F curve. Now we will talk about the steady state assumption or the closed vessel boundary. So a closed vessel is defined as one in which the fluid enters and leaves solely by plug flow, thus with a flat velocity profile, which means there is no velocity gradient. Now varying velocities or back diffusion, swirls and eddies, they are not permitted at the entrance or at the exit. Now at steady state, please note that the residence time distribution for any batch of entering fluid must be the same as for the leaving batch, such that no material of different ages get accumulated in the vessel, thus satisfying the steady state assumption. So at t is equals to 0, if a pulse of red fluid is introduced in the stream of a white fluid being sent in the reactor, the C curve of the tracer then would record the distribution of ages of that particular batch of liquid entering the reactor. So the RTD recorded, it should be the same for any other batch of the liquid at the exit stream of the reactor, but no accumulation as per steady state assumption. So your C curve can then directly give the exit age distribution. So this is the steady state assumption under which your E becomes equal to C. So if you see on the slide where the first picture shows a plug flow setup, so the second is your mixed flow and the third is your arbitrary flow. Now for a plug flow, here they have shown a step input. So in case of a step input, the exit, if it is a plug flow system, will also be a step change after the residence time spent inside the vessel. Then for a mixed flow, the curve would look like where it is shown as the F curve. The value is changing from 0 to 1. It will be exponentially increasing. So then for a plug flow, the pulse will be coming out of the reactor after the residence time shown here as T bar. Now for a similar impulse, the concentration profile or where the unit is, so it is a unit impulse. So then E becomes equal to C and the exit will be an exponentially decreasing curve. If you convert E in terms of theta, then E theta will also be equal to C theta in case of a unit impulse, and similarly your exponential function will also get converted into the dimensionless form of theta. Now, if it is an arbitrary flow, then what you observe may not be an exponential increase, but can be with many peaks. Similarly, for an impulse, unit impulse input, at the exit for an arbitrary flow, you may observe a lag as shown in the picture here, and with subsequent peaks of decreased amplitude can be observed coming out from the reactor, where the total area can be 1. Now, a quantity is subject to exponential decay if it decreases at a rate proportional to its current value. Symbolically, this process can be expressed by the equation shown here. Let's call it as equation 1, this differential equation, where the n is the quantity, lambda is the positive rate called as exponential decay constant. Your nt will be the quantity at time t, n naught is the initial quantity which is at time t. So, effectively the rate at which the n is changing is proportional to n, and lambda is your rate constant, and because decay, so therefore the negative sign. And a saturation curve will be represented mathematically as shown here. H is equal to A 1 minus e to the power of minus bt. So, A, B are constants, and this is an exponential function with respect to time. So, a saturation curve. Now, to characterize a distribution, what is important to be measured is the location of the distribution, mean value of the distribution, and the same thing is called as the centroid of the distribution. Now, for a C versus time curve, the mean can be given as shown here, and in terms of discrete time values, it can be shown here in the second line. So, this is how statistically you can define mean value of time in a C versus T curve. Now, the other descriptive quantity is the spread of the distribution, which we call as variance. Now, variance is mathematically represented as the function shown here. Let's call it as equation 2, and in discrete time intervals, it can be represented as shown in the second line. Now, for closed vessel boundaries at steady state, your E is equal to C. So, how do we practically find out misbehaving plug flow systems or those which are deviating from ideality? Now, if you see at the exit in a concentration versus time plot, something coming out after a certain amount of time, and the mean of the peak which is observed is found to be greater than the theoretical residence time. So, this shows reasonably good flow. It's a sharp peak, and the mean residence time is equal to the theoretical mean residence time. So, this T bar is the mean residence time calculated from the C versus T data, T bar observed, and T bar would be your theoretical mean residence time. So, if both are nearly same and you see a sharp peak in a plug flow system coming out with a time, mean residence time equal to that of the theoretical residence time, then it shows a reasonably good flow. So, no long tail if you see on the picture. Now, if there are stagnant backwaters, then your observed mean residence time would come much earlier than the theoretical mean residence time, and you will see a long tail at the exit of the material or of the tracer. Then in the third scenario, if you see many peaks of decreased amplitude, then this shows strong internal recirculation of the medium. This gives an indication of that behavior. Now, if you see only two major peaks coming at the exit. So, the earlier one can be speedy and the later one can be slow, where the peak can be, for one is less than the mean residence time, for the other is greater than the mean residence time. So, the one can be speedy liquid flow and the other fluid elements can demonstrate slow fluid movement. So, this indicates parallel paths inside the reactor or channeling. Now, if you observe a very late curve exit of the material tracer from the reactor, with the mean residence time observed being greater than the theoretical residence time, then this indicates either the volumetric flow rate or the volume have not been measured properly, or the tracer may not be inert, might be getting absorbed, or the closed vessel boundary assumption is not getting satisfied. Similarly, for mixed flow models, how to find deviation from ideality. Now, for an ideal or reasonably good flow in a mixed flow model for a pulse input, the concentration of the tracer will show an exponential decay, and your mean residence time observed would be equal to the theoretical residence time of the reactor. Now, if you observe that there is a lag and then you observe a sudden rise in the concentration with subsequent exponential decay in the C versus T curve, then this would mean that either there is a very long inlet pipe which indicates long lines for recording. So, either at the exit or at the entry there are long pipes. So, there is a lag due to this path covered by the fluid elements at the exit or at the entry. Then if you observed peaks, more than one peaks coming out at some intervals with decreased intensity, then this would mean inadequate mixing or maybe the draft tube effect, the internal recirculation. If your mean residence time observed is found to be early than the theoretical mean residence time, this would mean stagnant zones in the reactor, because of which the path being covered effectively has been reduced. So, most of the liquid particles are spending less time than the theoretical residence time. Now, on the contrary, if there is a late curve, which means your mean residence time observed is found to be later, much later than the theoretical residence time, this would indicate either incorrect measurement of the volumetric flow rate or the volume of the reactor, or the tracer is not inert. Now, very sharp early peak, this might indicate short circuiting from inlet to the outlet, and then suddenly it dies down. So, this can be due to the result of short circuiting. Now, whatever we have been spoken or we have derived up till now has been for a non-reactive system. Now, how can we relate the residence time distribution or this non-ideality, how will it impact the reaction or the performance of the reactor? Let's see and characterize that. Now, in order to characterize that, we need to determine how the concentration at the inlet and the concentration at the outlet are related to the mean residence time distribution, so that in case of a non-ideality, one can take into account what will be the actual reaction kinetics and the performance. So, in order to derive that, let us first see how C in and C out can be related with the residence time distribution or the E value. Now suppose we introduce in a vessel one short tracer. Let the signal be C in. And this tracer is not a pulse tracer, but it is an entire profile of C in versus T. So this is a curve signal. Now you can see it on the slide here. So this portion is your C in. Now while passing through the vessel, this signal may get modified to get the C out signal. So let's assume we were able to see this profile at the exit. Now since the flow with its particular residence time distribution is what is responsible for this modification of the curve of C in and C out, let's try to connect it with the RTD. Now focus your attention on the tracer which is leaving at time t. So which is shown here. So this is the fluid element marked as B, which is leaving the reactor at time t. So the tracer in this rectangle B will be equal to, so let's see this, so gray box. So the amount of tracer in this rectangle B, how do we determine? So the tracer which is leaving in this rectangle B fluid element is nothing but all the tracer entering at t prime seconds earlier than t. Now what was t prime? T prime is nothing but the corresponding element. It is the same fluid element which is in the inlet now being called as A, okay, and this grey box was your tracer element which is leaving here in the fluid element B, and this gap is t seconds earlier. So I'll repeat, all the tracer entering t prime seconds earlier than t and staying for t prime in the vessel. So whatever tracer we measure here at time t is nothing but all the tracer which must have entered the reactor before t prime seconds and which must have stayed in the reactor for t prime seconds. Now we show that the tracer which enters t prime seconds earlier than t as a narrow rectangle A. This was the same element at the before t prime seconds. Now in terms of this rectangle, the above correlation can then be written as, let's see, tracer leaving in rectangle B is equal to summation of all the rectangles A which have entered earlier than time t. So which means similar such all rectangles before time t. Now in terms all the rectangle A's which enter earlier than time t, the summation of all such rectangles having what? The tracer in all these rectangles multiplied by the fraction of the tracer in each of these rectangles which stays for about t prime seconds in the vessel. So not all the tracer here is spending only t prime seconds in the reactor. So among all these rectangles, the fluid elements, we need to find the fraction of those tracers which have spent t prime second inside the reactor. So this means what? That the concentration at the output at time t is the concentration of the fluid elements before t prime entering the vessel, residence time distribution. This is nothing but E t prime is the fraction of the tracer in the fluid element which stays for about t prime seconds in the vessel. So, this is nothing but Et prime as per the definition of the E curve. So, the fraction of the fluid element which is staying for the time t prime. This is Et prime dt. Now, here the integral will be all those elements up till the time t. So, the limit for integration would be 0 to t. So, we need to consider all the elements which have been entering and before time t. Now, with the law of convolution, this integral can be rewritten in the form of 0 to t c in t prime e t minus t prime dt prime. So, your C out becomes nothing but the exit age distribution multiplied by C in. Now, let us say it is reacting. So, mean concentration of the reactant in the exit stream will be equal to all the elements of the exit stream and the summation of all such elements, and summation of what? The concentration of the reactant leaving in an element of age between t and t plus dt, and the fraction of the exit stream which is of age between t and t plus dt. So, first we need to find out the fraction of those exit stream which are of the age between t and t plus dt and multiply it with the concentration of the reactant remaining in any element between the age t plus t dt, t and t plus dt. So, now in terms of symbols and the mathematical form, Ca prime by Ca naught. So, this is at the exit fraction of conversion. So, this becomes your conversion which is called as Xa. It is 0 to infinity, all the elements of the exit stream. So, we are having the limits as 0 to infinity. Now, for an element or a batch of fluid of age t, the second part of the summation is nothing but your E dt, and Ca by Ca naught is the concentration of the reactant at present fraction versus the initial concentration. So, this is your theoretical Xa multiplied by theoretical conversion multiplied by E dt with the integral 0 to infinity will give you the actual conversion. Now, for the first order reactions, we know that the product is related to the initial or the final concentration is related to initial concentration by an exponentially decreasing function in case of reactions, where Ca is the reactant. For the second order, it will take this form, and for nth order, let us say it is taking this form.